This part of the material is dedicated to matrices and solution method for the set of simultaneous equations. So the application of the finite difference method to Laplace equation leads to a set of simultaneous equations. And the efficient solution is a major problem in itself. For matrices of small sizes, one can solve the problem using direct approach in a form of matrix inversion or using Gauss elimination method. An indirect or iterative method are more efficient for matrices that are diagonally dominant, sparse, and large. Using an iterative method, a first approximation is used to calculate a second approximation, which in turn is used to calculate the third approximation, and so on until specific tolerance is attained. The three common iterative methods are Jacobi, Gauss-Seidel, and successive over-relaxation. And we are going to spend slightly more time discussing the implementation of successive over-relaxation next. So, in the absence of any educated guess, the value of free nodes can be set to 0. And now, uh, we raster the scan, and from top to bottom and left to right, and through nodes which potential can be determined. So this procedure is iterated a number of times so that potential at a node does not change much in the next iteration and remain within a specific tolerance. For example, if a specific tolerance is 1%, then the iteration is continued until this condition is satisfied. In numerical linear algebra, the method of successive over-relaxation is a variant of a Gaussian-Seidel method for solving a linear system of equations, resulting in faster convergence. So a similar method can be used for any slowly convergent iterative process, and in order to explain the main feature of the method of successive over-relaxation, let's consider its algorithm adopted to solve Laplace boundary problem. And again, we start with a matrix equation A u equal B, and we are looking for solution in this form. And to apply the method of successive over-relaxation in this equation 22, we first define the residual at node ij as amount by which a value of ij does not satisfy the equation 22. And we now introduce the notation for the residuum of this equation formulated for the node ij. And in general, the value of residuum, this r, can be negative, positive, or 0. And of course, equation 22 is exactly satisfied at node ij if r is 0. So according to the second equation, 22a, one can see that residuum r will change by -4 if the function u will be incremented by 1. And simultaneously, the residual evaluated at 4 JSON node, and it will increase by 1. So consequently, if we intend to reduce the residual r down to 0, it's necessary to add r over 4 to the function value u computed for this node, which is ij. So this operation will result in unproportional change of residual in the adjacent node. So reducing in this way residual r successively in each internal node, we can obtain more precise approximation of the desired solution. And after terminating calculation for all internal nodes, the process should be repeated from the beginning at the next iteration. So computational process organized in this way, relaxation methods is identical to the method of successive substitution, which in turn is particular version of Gaussian-Seidel method. So the term on the right-hand side can be regarded as a correction term, and the value of the residual at the case iteration, denoted here as R case, at ij, can be regarded as a correction that must be added to uij to make it near to the correct value. This convergence to the correct value is approach. The correction term Rk tends to 0. So the process of iterating repeatedly using the same equation for the nodal value is known as relaxation, from early structural application in which the process was envisioned as relaxing stress. An improvement that speeds the convergence process is known as over-relaxation. So it has been confirmed by numerous computational experiments that significant acceleration of convergence of calculation process can be achieved by changing the mesh point u by an increment greater than r. So method extrapolating this unique property is called method of successive over-relaxation. And seeking a possibility precise description of the relevant element, let's assume that the value of the function u can be obtained using this method in case and k plus 1 iteration, and for which we call uk and uk plus 1. So when the function uij is determined using the successive over-relaxation method, its discrete value in the k plus y iteration is calculated from this extrapolating formula. So to improve the rate of convergence, we multiply the residual by number omega and add that to u, and at the case iteration to get u at k plus 1 step iteration, we have this summation. So the parameter omega is called the relaxation factor, while the technique is known as the method of successive over-relaxation. So added weight of omega is intended to improve the estimate by pushing it closer to the exact value. And the over-relaxation brings an improvement as correction goes from iteration level k to k plus 1 is multiplied by this relaxation parameter omega. So naturally the convergence is speed of the iterative computational process that depend on the value of the coefficient of omega. So in the extreme case, when omega equal to 1, the speed attains its minimum, and the successive over-relaxation method transform into the Liebman successive substitution method. And then in order to start equation 22c, this is the last one. So an initial guess u naught is made at every free node. So typically we can choose u naught equal to 0, or we can take average of u as a fixed node. So the statement was proven by mathematician Ostrowski in 1947, and he showed that for matrix A, it is symmetric and positive define the method convergence of when omega is between 0 and 2. So we are generally interested in faster convergence rather than just convergence, and the choice of relaxation factor omega is not necessarily easy and depends upon the properties of the coefficient matrix. So the convergence rate of the successive over-relaxation method can be analytically driven but we operate with a number of assumptions. So then the convergence rate can be expressed in this form. Um, and the op basically the optimal relaxation parameter is given by this expression, and also mu here is a convergence rate of Jacobi method. So there are uh, various methods that adequately set the relaxation parameter omega based on the observed behavior of the convergent process. So usually they help to reach a superlinear convergence for some problems but fail for others, and that can be confusing. But I would like to say that relatively simple statement. When we have omega equal to equal larger than 1, uh, then we can use it to speed up the convergence of a slow convergent process. And at the same time, values for omega less than 1 are often used to help establish the convergence of a divergent iterative process. So evaluating the optimum value of omega for, for which most of the rapid conversions can be achieved is a rather complex issue. There are several specifics that one can mention about the choice of omega in this method. So the value of omega lies between 1 and 2, and basically the relaxation factor omega is selected such that omega is somewhere in between. So if we assume constant omega, which is known as the relaxation parameter, then we can also use equal to 1, and then values of omega greater than unit speed convergence, but too large value of omega, it results in numerical instability. So omega larger than 1 improves the convergence, but the stability reason because of the stability we need to take omega less than 2, and when omega is just equal to 1, the method is simply called successive relaxation, right? So we don't have over relaxation, and its optimum value omega output must be found by trial and error. So basically the choice of proper value of omega is dependent on the problem. In practice, omega optimum is evaluated most frequently from this formula, and here we have I and J. They are maximum indices of the applied rectangular grid. And further, for Laplace equation, a trial and error estimate for the optimal value of omega varies with the number of grid points in the direction n, and omega optimum would be defined as 2 minus c divided by n, where c is an independent number that depends on the geometry. And for Laplace equation, the value of 2 gives instability, and the value near 1.5 are shown to give good results.